For those of you who did not get a chance to do the VOA tour on Thursday, you missed a really neat station. There's a 10 gigahertz station that Mike and Jim Miller have put together using a surplus dish down there, and it's quite cool. So we're going to hear about it now.
Yep. Oh, I'm wired. Where's the remote thing? Is that it?
That's it.
Okay. Oh, does it? Well, I got this whopper here. Okay, well.
That's one you pointed at.
Yeah, that's right. That's what Miller was telling me. Well, I'm Mike Murphy, KA8ABR, and my compatriot there, Jim Miller, is sitting behind the projector. He's N8ECI, and we got involved with converting a commercial dish that's at an old Voice of America transmitter site down by Cincinnati, put it on 10 gigahertz EME. So this station was actually built between 1942 and 44, went on the air in September 44, mostly as propaganda into Europe during World War II. Then when the Cold War began, after World War II was over, the station stayed on the air, and in the 60s they modified it, put in newer curtain arrays, and mostly aiming at Southern Europe and Northern Africa when it got to be named, where's the pointer? When it got to be named the Relay Station. So they became the Bethany Relay. Bethany is a little town near where this is located. This is just north of Cincinnati, right along I-75. If you guys remember years ago going to Dayton, you'd see that all the big rhombic arrays, and that was this site. All that was dynamited down. The station went off the air finally in 1994, and then they dynamited the towers down in 1997 as part of the effort to reclaim the site. Then the site was donated to the local township that had like 400 and some acres. So this part of the transmitter building area is the last part that belongs to the township. The rest of the land was given to the county, and they've made a big soccer metroplex thing kind of out. There's a lot of soccer fields out there. Nothing left of the antennas except some of the big concrete bases that were put in the 60s for the curtain array. But before the station went off the air in 1990, the Voice of America decided to put in a television satellite system. So instead of using audio coming over telephone lines to the site, they decided to use geostationary satellites. So they put this KU band system in that it transmitted and received. So the site would never had a microphone here. Cincinnati had a big German population. They were afraid of fifth column movements. You know, the machine gun was up in there. And this site was guarded. There was never a microphone on this site, so that they figured a fifth column movement could occur, and the local Nazis could start sig heiling in the parking lot and transmitting. So that tradition continued. There was never any program developed here. It was just sent in from Washington. So they had a transmitting set up on this thing to send the signal, the monitor signal, back to Washington. And that was put in 1990, and then in 1994 the station was taken off the air. So this is a 24-foot Vertex radiation systems dish, and put in with a big Kingpost Mount we'll talk about, and then behind it's like a truck body enclosure that's insulated and has big air conditioning on the ends because this was full of equipment. And basically when the VOA left the site, they stripped a lot of stuff out of this. They took all the transmitting, receiving equipment. They took the motors off the actuators, the big actuator drive, you'll see that. And so basically, you know, it was kind of a shell when we got it, and the dish wouldn't move, and it had been abandoned for, I guess we started on it in 2005, so it had been sitting for about 11 years. So it was about 2005 we started cleaning the junk out of the box there, and trying to decide what to do with it. I'd seen this thing. My great uncle used to work at this station a million years ago, so I'd go up there and screw around and watch the big transmitters and that when I was a kid, but that's long before this was put in, and so I didn't live in the area anymore, but every once in a while when I go by, I'd see that dish. So I met Jim through other activities, and I said, hey, and he's made some comment about being involved with this WC8VOE group, which was the radio club there at the Voice of America transmitter site. So I said, hey, what about that big dish there? Because I always collect the big dishes. You know, I've got them sitting in 3 states, you know, on the ground. But and so we figured out that we couldn't really take it, but we could probably use it there. We got permission from the local authorities to actually modify the antenna and use it for moon mounts in association with the activities of the local club. So, of course, with microwave basics, we decided to stick with 10 gigs because we discussed maybe taking the secondary reflector out and putting a prime feed up there. I had one I got from W2DRZ at Dayton years and years ago, so I thought, well, we could do that. But, you know, then we'll mess up the alignment of that. You know, the guys that maintained the dish kept the optical path line very well. So we decided, we'll go ahead and do it on 10 gigs. So we started gathering equipment together and looking at some of the requirements. Of course, you need high transmitter power, but that was hard to do at 10 gigs back then, except with traveling wave tubes. You want a low noise figure as possible, large antenna aperture. When you go to large antennas, though, your beam width gets tight and you start having pointing requirement issues. I'm sure everyone's aware. Of course, you need to keep losses to a minimum, so we're going to be doing some things with waveguide instead of just coax. So basically, the system we came up with is, come off the dish, go through a waveguide switch, through a DB6NT preamp that I'd gotten through a white box project. I bought a bunch of white boxes, a local club here that put it on this event, bought a bunch of white boxes from Jeff back in, I guess, the early 90s, 2000 or so, yeah. So I had Gerd had gone to Germany and brought a bunch of those back for us, and then we were advised to put a little bit more gain behind it, so we got a down east preamp behind it, and then we go into a down east, oh, look at there. Look at that. See that? See, I'm from the aeronautical world. I'm not an electrical engineer, so I learn everything out of the Rad Lab books. So guess what they call it? Kilomegacycles. So we go into this transverter here using a 2 meters as our IF. We've got an ancient IC251 here from Red Dakin, WLUC or ULC. I bought that from him, and he had already modified that to put out maybe 10, 20 milliwatts for transverter drives. So that was ready to go. Then, of course, we use a PC running the Spectran software that looks at the audio coming out of that to give us some spectral information or waterfall display. Then we'll discuss this a little bit later. We have a noise indicator that we use. Of course, we have a variety of synthesizers right now. There's a 160 megacycle, what was it? PSI, right? PTS is in there right now. But we had a G4HUP synthesizer in there for a while that worked, but it's having problems. So Jim had one of these things we got in there. But we also have a Z3801A GPS discipline oscillator there to give us 10 megacycles for locking things up. And we have a transfer switch that's next to the transverter so that we can either use the down east local oscillator chain that's inside the transverter, or we can break that out and come out and use our lock sources to be on frequency. From there, on the transmit side, we go out to one of these down east 2-watt amplifiers, and then into a Siemens 1189 30-watt, we're getting 30 watts out of it now, traveling wave tube amp back to the waveguide switch and out. Then we got a sequencer here that I won at the 2004 EME conference in New Jersey, so that was our door prize finally gets used, and we have a TX command that just comes from an old J38 key. So this is basically the RF equipment we decided to put together for this system. And this is what it looks like today. I'll show you some pictures of the back of the dish. The dish has, it's all insulated because it was for KU bands, so when ice forms, that can attenuate the signal. So there's big electric heaters in behind the dish to melt that out. So there's an equipment compartment in the back of the dish where normally this, this tray would sit. So since we've been experimenting with the trailing wave tubes, we brought everything into the little shed because we didn't want to have the high voltage and the power supply for the tube out in the back of the dish. So this is elliptical waveguide. I think we got that from you, didn't we, Jeff? Yeah, I think we got that from Jeff. And there's like 20 feet of that or so that goes out in the back of the dish, hits the feed system of the dish. The traveling wave tube amp is right there. Power supply for that is here. There's a Z3801. Then we have some EH tuners here and some power sampling to come off. This is the waveguide switch in here. Back here, the receive preamps. It's sitting on the transverter there. Here's the coax or the waveguide coming out of the tube, heading down here to go out to the dish. Excuse me. We decided to use the original feed horn that was in the dish. It turns out that radiation systems said this thing cuts off, down around the 10 gig area. So we thought, okay, we're hams, we'll just try it, right? So we just went ahead and tried it. But there was an ortho mode transducer there because they were using circular both polarizations for transmit, receive, duplex. So we took all that out. We found out that 3/4 inch water pipe, copper water pipe works good. And then Jim made some transitions here. There's not a transition, but an end coupling that with some plumbing fittings to go to a 4-bolt flange to fit. This is a termination, a probe that was made to pick off the 10 gig signal. We're not using that right now, but we do go from the circular there to rectangular. So we applied that Cruthism that you've heard a couple times today, that if you do things gradually enough, the microwaves don't mind. So in the vise with some copper and bending around, we kind of formed a circular to a rectangular transition that seems to work. You know, yeah, exactly. That's what it was, right? Beer and hit it and go. You know. So this is the original feed horn. It's a conical ridged horn there that sits in the base of the vertex of the dish. So that's kind of what the feed looks like, and we're still using that. Then the big thing with this system that we ran into trouble with, and a big complication, is actually moving this dish and pointing it. So the thing has some big joist actuators on it that are just big versions of what you saw on C-band dishes 35 years ago in the backyard, just a big motor-driven screw. And it has anti-backlash capability. They're big, they're heavy things. I wouldn't want to buy them new. Those were still in operable condition, but the motors and gearboxes were taken off. So I think Jim bombed up the Mendelsons. Everybody knows where Mendelsons from Dayton, you know, the big junk heap here in Dayton. Got some gearboxes and some three-phase motors. So our system, you know, there's the dish. We have the actuators. We actually use three-phase motors and speed-reducing gearboxes to drive the big jack screws. We have two commercial off-the-shelf variable frequency drives that drive one for each axis. Each motor is independent. And then we've got a Unix program running in a PC that actually does the feedback effect, where when the dish moves, we have optical encoders on each axis. Originally, the system used Selsons, and they had 4-to-1 speed increasers with anti-backlash gearing in it. So we took those off and put encoders on, and they're not absolute encoders, but they do have a calibration mark. So there's an encoder interface that Jim designed, and we had help from a friend of ours that builds circuit boards and circuitry for a business, and he helped us with Eagle to build the board up in the CAD program and make the board. So then we use the time signal from the 3801 through the Windows PC using W9IP's old program, Nova, to generate the pointing angles to the moon. And then we were having some accuracy issues, so we thought, well, we'll take a look at what JPL, you know, what Caltech's Jet Propulsion Lab, they are responsible for tracking all these deep space objects that they launch, as Jeff mentioned. And they actually give ephemerides for these things that are fairly accurate. So we just kind of compared what we were getting out of the NOVA program to what we were getting from the calculations of position of the moon from JPL, and NOVA wasn't that far off, so that wasn't our issue. This is the optical encoder interface box that Jim developed here. You know, so you bring the signals in from the encoders and do some level changing in that, and then there's a PIC there that does the looks for which way the dish is moving and gets the count right, and then puts it out on RS-432 here back to the PC. Then this is underneath the dish here in the back. If you were on the tour there, you saw a big white box under there. I got that when I worked for a gas engine company here in Springfield, Ohio. When they went out of business, man, I grabbed a bunch of those. Those were going in the dumpster. So we used one of those to hold these off the shelf. These are Automation Direct variable frequency drives. They're, a couple $100 now for one horse drive, and they talk over the RS-232, and they have all kinds of options. You can accelerate, decelerate, they have regenerative braking if you need it. We didn't need any of that, but it was an interesting way to actually make the dish move. Of course, it's cast grain optics. We'll spend a lot of time on this, but we have a secondary reflector out here. Feed horn is behind that, up against the vertex of the dish. You know, the rays from infinity coming in parallel, hit this hyperbolic secondary, run into the focus. Got popular with space communication because your feed horn, the spillover, is looking out into cold space. So instead of having a prime focus where you're looking back and spillover past the dish is looking at the hot Earth, you're looking at cold space. So it increases mechanical stability because you don't have the secondary way, or the feed way out here. You're back in tighter. You know, it moves all the electronics back here in the back of the dish because your feed is right there. If you saw that picture of the feed horn, big long pipe coming back there, comes back where we used to have the electronics here. And it's easier to, you get a shallower angle of illumination, because if you have a very steeply curved dish, you got the feed in close, you really have to spread that RF out to feed the edges of that dish. And that's somewhat difficult to do. So now you have this smaller subreflector sitting out there, and you can almost use like a W2 IMU type dual mode horn to feed that because you got a narrower angle. But the disadvantage are you actually, you actually block some of this here. So some of this area that wouldn't have been blocked by a smaller prime focus feed is blocked by that secondary. And then you get this optical alignment problem that I was worried about in the beginning. Is if we took the secondary out, we might not be able to really get that back in position to restore the optical alignment and get the optical path right. So for space communications, the advantages outweigh the disadvantages, and of course a lot of times Uncle Sam's paying, so who cares? So then we did some calculations on what our band beam width might be and possible gain. And you crunch through the numbers and you come up with a theoretical gain of 61 dBi. So practically we're probably about 50. I don't think we ever really measured it, but it's pretty tight. Say again? I always be very conservative. I'm not a good salesman. I do this for fun. I work on jet engines. I don't have to worry about it. Yeah, we saw. I remember that. And there's luckily not much information was left at the site. The site was all cleaned up, but we found some paperwork from when this was installed. They had beam pattern plots where they swept past satellites and got the beam pattern on it, and I think there was some gain information in that. But I mean, I think it's hard to measure, so it works. Then we have this Kingpost mounting system, which becomes a problem with trying to use this dish for EME communications. What that means is a big giant post back here that holds the mass of that dish, and there's these backstays that hold that up. It's kind of a degenerate mount. This was developed to just make mounts simpler and cheaper for television applications where the dishes only have to look at the Clark belt where the geostationary satellites sit. So it's kind of a degenerate, cost-reduced way to do it. You don't need to have all the complication of an all-sky system where you got to move the dish through zenith or go backwards or go all around like Jeff's dish. So here's a side view of the thing. You can see here, this is the insulating panels on the back of the dish. The heating elements are inside there. This box you can barely see here has the big contactors to turn those on and off. We don't turn those on and off. We generally don't have a problem with ice. We're not there when it's that cold, and we don't want to slow the streetcars down. So there's the Kingpost there. And it pivots on this axis here. I used to always say that joke, but unfortunately Cincinnati has actually developed a street railway again, so my joke has to be tuned, I guess, because they actually do have streetcars in Cincinnati again. But they don't look like a streetcar. They look like some European train. But anyway, there's the pivot axis where the antenna can pivot in azimuth. These are the backstays that take the reaction to keep that thing from falling that way. And they're bolted in hard to the place where the bearing is sitting. So one of the problems with this is it limits the azimuth you can reach. So in essence, we can only, oh boy. There's the elevation jack there that moves the dish up and down this way. There's the azimuth screw jack there. They're pretty big. It's got a boot on it that covers the Acme screw that runs through a gear that's driven by this equipment here. This white tube is where the back side of the Acme screw will go to keep it protected from weather when the dish is moved over to the east. Right now, in this picture, it's moved way out around to the west. And then up here, you can see this is the bottom pivot axis. You can see there's a little track here. There's some stops there where you can use micro switches to limit the travel and stop before you cram things mechanically. The little gearbox and the enclosures where the cell sensor is here, so we've got the optical encoder in there now. And then this is one of the junk motors from Mendelssohn's in a junk box. So if we use the radar view in the old NOVA program, I don't know if people still remember this program or still use it, but if you use the radar view, we're kind of looking down from infinity down towards Cincinnati, and it gives you like the old PPI screen. So the mechanical limitations of this dish mean that we can only see this part of the sky here. We're limited to 120 to 240 degrees about azimuth. So we can only see this pie-shaped area of the sky, which means that during contests, because 90% of the activity now is in Europe, so the contests occur when the declination is very high, and the moon is running up in this part of the sky. You can see that moonrise is over here when it's high declination, so Europeans are on here, but by the time we get to here, where we get the moon, it's been up here for like hours, and they're either done, too tired, or they're so drunk they can't stand up, so we can't work them. So we only get the moon for a couple hours here. So that's why you don't hear us on during these contests, because we have very, very limited moon access, and the Europeans are done long before we get on. But if you were there for the demonstration Thursday, the situation you see in this picture was true. The moon right now is at a very, very low declination, which means it's very far south below appears south below the celestial equator, which is just our equator projected to infinity. So what that means is now we get the moon for a long, long time. So when the moon's very far in the south, it sweeps through this part of our beat, and we get it for hours and hours and hours. So the other day during the tour, we actually got the moon around noon and lost it around 8 p.m. So this is one of the limitations of using this kind of system, but Jim and I looked at maybe trying to modify this mount, get a little more range out of it, but we had to jack up a 5-ton dish and put scaffolding under it and hold it all together and then do a lot of massive fabrication and all that and some big work. And there's political issues at this site. You know, the local township still runs it. We're lucky to be there, so, you know, we didn't want to have Sanford and Son construction company over there doing all this, so we just decided to kind of leave it be. Some other projects we wanted to do beyond moon bounce would still be practical to do with this kind of thing, so we just decided to leave it alone. So the activities, I just, you know, remember I had to put this list together a long time ago. It's been a long time since we got started with this, so you'll see that Jim's call shows up a lot because he did the lion's share of work on this. You know, so his capabilities of machining and computer programming and, you know, having a lot of test equipment, that really made it an easygoing project because of his efforts. Jeff here was very helpful. Jeff's knowledge, of course, the Cruthisms, we depended on those and suggestions. And then, of course, unfortunately, Dave Powis here at G4HUP is a silent key now, but his son moved into this area, had married a gal from this area, so his son lived here. So Dave would come over from England a lot to visit his son. Well, when he was bored with that, he'd come up to the VOA.
Wasn't it Dave that came down and tested the amplifier for you guys?
Oh, yeah. Yeah, he would come down with us, yeah. So he was here quite often, and he was really an asset, and he's the guy that, you know, had a lot more experience with microwaves than Jim or I did. You know, I'd read a lot about it, but this is kind of my first big microwave project here, and I think Jim too. So Dave's experience, you know, he's the one who encouraged us to put more gain behind that first low noise amp, the DB6NT amp. So, and then Dave also, he's the guy that put together the noise meter for us, you know, that was a G4NNS design. What that is, that's just a regular, like a TRF, 2-meter TRF receiver that has like a 2 megacycle bandwidth, you know, so that we're just going to use that as kind of like a radio astronomy receiver that you would use to pick up continuum type signals, and we'll talk about that in a minute. So, so this was 2005, 2006. Because it was already a TV thing, it was easy just to slap an LNB on there and take a free-to-air receiver or one of Jim's spectrum analyzers. So we could do a lot of work with pointing and getting this system running by using the free-to-air satellites that run along the Clark belt, you know. Of course, there was one up there with a fashion TV, you know, a supermodel channel. So if you look at our calibration, 00 is where Galaxy 19 used to sit, you know, because when the thing goes cuckoo for Cocoa Puffs and loses its brains, you got to move the dish physically through where the encoder will let the computer know that it sees the calibration mark, and that was Galaxy 19. So anyway, so we first detected moon noise in September of '06. You know, I think that was with one of your spectrum analyzers. We started being able to track accurately enough to find the moon, and we said, oh, there it is, you know, because cold sky, bright, you know, warm moon, you could see it on the spec end. And then, so because we were starting to have some issues with the pointing, we decided to go ahead and build that box. So basically, Dave at G4HUP put that together. I think he did it at your house, didn't he, Jim? Yeah, so we used to meet over at Jim's place and work on a lot of this stuff. And then, of course, on November 13th, Al Ward was made a contact with us. So we were able to, he was the first guy we heard off the moon, and we made a contact with him pretty quickly. And we could see that he was about 15 dB above the noise based on the Spectran software, so it seemed to be working. We kind of played around with the polarization system in there. Since the dish can be put anywhere, you know, and since it doesn't track, it doesn't have a polar mount. You know, the old things you saw in people's backyards had a polar mount. And if you ever watched how that moved, you know, if you had something horizontal over here or like line like that in the east, as it went to the west, you'd see that roll over. And one advantage to doing that is you maintain alignment with the horizontally polarized and vertically polarized signals coming from the satellites. So if you remember your old C-band system from 35 years ago, you could move one satellite to another pretty close, and you didn't have to do much with your polar rotor. But if you went all the way across the arc, you had to play with your polar rotor a little bit, you know. But this system, since it doesn't have that capability to maintain alignment because it's not following the polar motion of the Earth, and turning along the Earth's spin axis, you always have to kind of correct that. So RSI put a big system in there that would turn this whole back of the feed with a bicycle chain and another motor and that. And so we got that going to play with polarization, but we didn't see a whole big effect with that. We didn't really notice any big differences, so that's kind of probably rusted up again. And then to just get a little more frequency stability, David come up with a rich, kind of a rich, spiky synthesizer idea where you could actually lock to a 10 megacycle signal on like 100, and I think we're at 183 megacycles or 189 is where we drive our local oscillator chain. So that was the first time we had really good frequency stability. And that was in March of '08. And then the last thing we really did on the station was March of '09, we started playing with traveling wave tubes. And since we were getting less active with it, and around here it's very humid, we didn't want all that equipment sitting out in the back under the tonneau cover behind the dish, so we moved the tray into where you saw it in the photograph there. It stores better in there. Now, we've got probably we've added probably, a dB of noise figure with 20 feet of elliptical waveguide. So maybe we're down a little bit on receive, but we just haven't been working a lot of people. But was it back, I think it was April or May, we were on, and some of these digital guys in Pennsylvania, we could see them. So, I mean, they don't run a lot of power and have small dishes, but we could see the 4 streaks. So we still, even with all that waveguide in, we still could see, kind of weak signals. So it still works pretty good. And I think that, when we first got going, we figured we could see about 22 dB of sun noise based on using a spectrum analyzer, and we get about maybe upwards of 3 dB of moon noise. So one thing that's bugged us the whole time is the pointing issues. Now we get like 0.018 degree accuracy off of our optical encoders. In this dish, one thing about a Kingpost Mount is the dish always points down, well, on this side of the equator to the south towards the Clark belt. And so you never have to go beyond overhead. And so a lot of the overhung mass of this thing hangs out there. So the bearings are always loaded up. There's no slop in this system. The big actuator screws have anti-backlash gears in them so that you never get this looseness when a gear stops being pushed one way and has to turn around where you get this slop. So it's a very, very tight system. Some guys have a balance system where you'll see the big dish and then they'll have the barbell weights or, truck rims or whatever out here to balance it. Well, those get into a problem because when they move to certain angles, they have load reversals. So any slop in the system will come out. And you'll kind of see that sometimes on pointing, but we don't have that issue. So we kind of figured out, well, we can watch the moon, we can watch the sun. We know where it should be. We find it with the noise meter. Now, what's the error there? So Jim changed his program for the pointing where we could put trim factors in there. So you can actually off point and find the moon. And that was what we needed, that the noise meter, this guy, because we'll actually get pretty close. The system will drive where we think the moon should be based on the NOVA program. And then we have to kind of, Helen Keller it and hunt around, move around until we find the noise peak. And then once you're kind of on it, she'll track okay for a while. And then you'll notice that the noise will drop off a little bit, so you tweak it up again. So we started taking data to try to figure out what was going on. And it's been kind of a mystery that might be coming to a solution here. So we wanted to develop like a correction table or some sort of an equation. 5 minutes? Yeah, I'm almost done, really. Okay. So, we tried to develop a correction table so that we could, use this data we've been collecting over the years to come up with lookup tables. If certain azimuth and elevation, what would the correction be for those two axes? So we found out that by just plotting the data, it's nonlinear and it's variable. So it changes year to year. And we've been working on this thing for 12 years, and it's always kind of been a secular type of a problem where the error isn't really not linear. I took a big simplex jack down there and jacked that sucker up, tried to see if I got any slop in the bearings, and it's still tight. I couldn't get any slop, even though I'm trying to pick up 6, 7 tons. I brought a 20-ton jack or something like that to get that up. And so we also could use geostationary satellites to accumulate data along the Clark belt. So we plotted some of this stuff up, or Jim did the other night, and you can see that these are the data points. This is, in this case, it's azimuth, so this is the degrees of azimuth. Of course, it goes 120 to 240 because that's all we can see. And these are actually observation points, and these are only the moon. So we just added some data that we've taken this year This is the correction factor over here that we have to add to get back on the moon, closing the loop using that noise indicator. But you can see it's not very linear. And we just added these points the other night. We knew we were going to give this tour for this group, so we went over there a week ago or so and got the system going, but we didn't have moon. So Wednesday night we were back over there, and we actually had moon that night. So we added these points. So you can see it it's not very linear in its curves, and these curves change over the years. And this is back in December 2017, so you can see the curve is behaving a little differently. The scales are a little bit different, but you can see we're adding just a few more data points, really changes the shape of these curves. And the one for elevation shows a similar type of behavior, where what we got just a few days ago by adding, this is old data and this is new data from the other day, because, or actually I think this is new data here because the moon wasn't very high the other day. You get the same kind of thing. You got this like cubic function when you curve fit this data. When you curve fit this data, you get this cubic function here. So it's not very linear. So I've been kind of pulling our hair out about this, and I got a lot to pull out. So for years, and then it turned out that the random error suggested it wasn't very mechanical. And with all our checking of mechanical things, we decided that's not mechanical. But then one of the guys used to work at the station that volunteers there now. We were talking to him. This has been a while back. He says, that big concrete base under that thing, there's a big concrete pad down here, under here. And I just make an assumption that this has got goes down 15 feet and there's 12 yards, 20 yards of concrete down there. Get a good solid footing. He says, oh no, that's only 3 foot thick. I'm like, oh my God, that thing's just floating. So there's no real good connection. So with the freeze and thaw, my theory now is with the freeze and thaw, this thing kind of randomly moves around and it tilts. The axis that's supposed to be vertical is actually tilting in 2 dimensions, and causing us, I think, a bunch of grief. And the VOA TV system, he told us, he said, oh yeah, when they put that in there, they'd lock onto one satellite, and every hour it would go down in elevation, up in elevation, left in azimuth, right in azimuth, find the peak and go back to it. So they didn't need to have any stability mechanically, because every hour this thing automatically corrected itself. So if you took the tour, even though it's kind of hilly in southwestern Ohio, it's really dead flat there. And even though that's the highest point of southwestern Ohio, it's one reason Powell Crawley bought all that property when he put the WLW up there. He wanted a high takeoff angle. So it's still flat and it was really muddy. And if you saw it the other day, we hadn't had rain for a little while, but it was really muddy there. So I think that our conclusion here in the theory right now is that we've got this freeze and thaw issue. So we're going to have to maybe come up with this correction table and take a lot of data and update it pretty readily to be able to trust the mechanical pointing of the dish. So, any questions? That's about all I had because we have a short time here. Yes, sir?
What's your maximum elevation for that zone?
Dead overhead. We can go bird bath. Yeah. But when we're up there, we got very little moon. But the moon doesn't get that high here. Yes?
You got any accurate pointing areas nearby, like say the Congress building itself? Use a little optical satellite track pad again. But something else is really stable.
Unfortunately, where the transmitter building is, we can't get over that far. And we've got a little hut out about, 100 yards, 120 yards out. We got a hut where we could put a surveyor point there. But we haven't. What we usually do is just use the geostationary satellites. We know where they're at, So those are good. Yes. No, we haven't really considered that. Now, one thing I wanted to do, and we got jobs again and we're busy, but what I wanted to do was actually put an optical telescope. I got several, small. No, what we want to do is line up on a geostationary satellite and then find that satellite with the telescope. And you align the radio axis with the optical axis. Then when you... Yeah, and we do come down low because the other night we were right down low, but we didn't correct for that. You mean there's just a straight correction for that? Just refraction, yep. But see, yeah, and stay on that noise. But see, you can see we get a lot of the elevation data is up pretty high. and see we still have this problem even when it's up real high where you're not looking through much atmosphere. But that is something to consider. I mean, even when we're up at 50 degrees, there's probably some sort of correction that we haven't taken in. But, and that's nonlinear, that's secular, so yeah, that might be a problem too. So that's something we could look at. Anything else? Yes, sir.
Yeah, Mike, what'd you use for encoders?
Just junk out of Mendelssohn's, wasn't it? 1 horsepower, 3-phase.
No, encoders, not the drives.
Oh, encoders. Yeah.
Yeah. What was that? Okay, all right, very good. I wanted to thank you guys for putting together the tour for us. Appreciate that. I hope these guys had a good time. Thank you.
You're welcome.